Saturday, March 14th, and this is Nighttime Mathematics Radio. Now, if you haven't been on Nighttime Mathematics Radio before, the format's pretty simple. You tweet your math questions to @NightMathRadio on Twitter, and I try to answer them here live on YouTube. Now, the live recording for the show actually didn't make it quite well, because unfortunately, we had a bit of problems with the last night's live recording. We discovered that our bandwidth had all gone away, and the audio didn't work, so we ended up with the most boring math video ever made, and that's something of a challenge. So, we'll re-record it here tonight and send it on so everyone can see what happened. This is Nighttime Mathematics Radio. Now, we got two questions over the course of the week, which we'll answer tonight. But a quick reminder before I go on to the questions. It's become a very strange shut-in world here at Night Math Radio, because between coronavirus and every school system shutting down, but keeping all the math homework intact for some reason, there's a whole world of people out there with lots of math questions. We'll try to answer them here on the air, so every night next week at 9 p.m., we'll be posting a new episode. If the internet cooperates, I'll do them live. If not, I'll do what I'm doing right now. I'll record them ahead of time and post them at 9 p.m. This is Nighttime Mathematics Radio. So, we had two big questions come in over the course of the week. Question number one was some linear algebra, which we haven't had so much of on the show so far. And the question looks like this. Suppose you have a linear transform from T, which goes from R3 to secondary polynomials, defined as following. XYZ is mapped to... XYZ is probably a bad choice, isn't it? Let's call it instead ABC. ABC is mapped to A plus B x plus the quantity 1 plus C x squared. So let's spend just a moment talking about linear transforms and what they are. So the question we're trying to answer here is this a linear transform? So first question is, what is a linear transform? Well, a linear transform is a mapping from one vector space to another that respects the properties of the vector space. And what do we mean by this? Well, first of all, what do we mean by vector space? Well, each of these things up here are vector spaces. What a vector space is a space where each value has... where the values in this space support two basic operations. They have to support addition, and they have to support multiplication by a scalar, that is, multiplication by a real number or a complex number, in this case real. So let's take a look at this. What do we mean by... Well, suppose we have these kinds of numbers, say A1, A0, A1, A2. If R3 is the space of ordered triples like this. It's a space... essentially of points in the three-dimensional space, where we have an x-coordinate, a y-coordinate, and a z-coordinate. How do we add these things? Well, we just add them element by element. B0, B1, B2. If we want to sum those two vectors, you just sum in each component. A0 plus B0, A1 plus B1, A2 plus B2. And you also have to support multiplication by a real number, and that's also easily defined. If lambda is some real number, you could just multiply it into each component. That becomes lambda A0, lambda A1, lambda A2. And in case you're having trouble seeing with all these variables, let's look what this looks like with actual numbers in place. Suppose, for example, you have the point 1, 2, 3, and you want to add the point 4, 5, 6. Well, you just add it element by element. 1 plus 4 is 5. 2 plus 5 is 7. 3 plus 6 is 9. Suppose I want to multiply 1, 2, 3 by, say, pi. Well, just multiply it in element by element. That becomes pi, 2 pi, 3 pi. Straightforward enough. How about P2? Remember, the space we're mapping into is P2. This is the space of polynomials, and it's often written P2 of R. P2 polynomials over the real numbers. That's just literally every polynomial that goes up to second degree. So that's everything of the form, say, a0 plus a1x plus a2x squared. And this space has really obvious addition and multiplication. They're just the standard addition and multiplication you have for any polynomial. If you add them, you add like terms. If you multiply them, you multiply in each case. And the cool thing is you notice this looks a lot like R3. You've got your three coordinates, just like before. The multiplication rules work the same way. The addition rules work the same way. So these spaces are really closely related. Now the question is this mapping up here a linear transformation? What does it mean to be a linear transformation? It means you respect the rules of the vector space. What I mean by that is, for example, if I'm doing the transform on a multiplication, a0, a1, a2, it can't matter whether you do the multiplication first or second. This should be the same as lambda times a0, a1, a2. Oops, lambda times the transform of a0, a1, a2. Ha, that's better. So in other words, it doesn't matter whether you first do the multiplication, then apply the transform, or if you first do the transform, then apply the multiplication. It has to come out the same way either way. Likewise, if you're doing linear transform of a sum, transform of a0, a1, a2 plus b0, b1, b2, if it's a linear transform, it should come out the same as if you first did the transform to each vector and then added. Now it turns out, if you look at this transform, it fails spectacularly at both. But let's take the easiest one of them all. For a linear transform, what can the linear transform of the zero vector be? And notice every vector space has a zero vector. It's whatever zero times that vector, any vector in the space is. It's the additive identity, because we said we had an addition, so there must be some zero vector. In R3, it's 0, 0, 0. In second degree polynomials, it's the zero polynomial. And this has to map to 0 in the new vector space. How do we know this? Well, because, remember, it respects multiplication. T times 0 times any vector you happen to have, a0, a1, a2, has got to be equal to t of the zero vector, because 0 times anything is the zero vector. That's easy to prove. But because, remember, linear transforms respect the vector space properties, the 0 you can pull right out of the transform. This is some vector in the new space, and that also has to be 0. It has to be the zero vector in the new space, in the domain space. So the question is, does this transform that we see up here respect this property? And the answer is, no, it really doesn't, because 0, 0, 0 maps, which is the zero vector in R3, maps to 0 plus 0 times x, so far so good, plus 1 plus 0, which is 1x squared, so it's just x squared. So this transform doesn't respect the vector space properties. It doesn't respect multiplication by a scalar. It also doesn't respect addition, which is easy enough to check. If you take two of these things, and let's pull up a new page real fast. But if I take t of, say, a, b, c plus d, e, f, that's going to be t of a plus c, b plus e, d plus f. So that's going to be equal to a plus c plus b plus e x plus 1 plus d plus f, because remember that was the x squared, that's the definition of the transform. But t of abc separately is just a plus bx plus 1 plus cx squared. T of def separately is d plus ex plus 1 plus f x squared. And now you notice we have two 1x squareds. So when you sum those up, you're not going to get the same thing. You'll get the same constant term. You'll have the same first degree term, but the second degree term is now going to be 2 plus c plus... Oops. I completely lost my mind apparently somewhere in here. A plus d c plus f. That's embarrassing. C plus f, b plus d. There we are. So you notice this is not the same thing at all. Here we have 1 plus c plus f. Here we have 2 plus c plus f, and those are totally different. And that's a bit of a problem. So in this case, this is not a linear transformation. Okay, what was the other question we were asked over the course of the week? And the question came up with somebody who's trying to understand how you go between the two different forms of a quadratic function. We're going all the way back from linear algebra to high school algebra here. But in high school algebra, when you're looking at quadratic functions, you're usually shown them in two ways. You're shown them in this form, which is called standard form. And this is typically the result of simplification. This is what you usually use algebra to do, is to get things into this form. It's a great form for working with a function. It's not a great form if you're trying to understand what the function is telling you. For that, you need a different form. If you're trying to understand the function, you'd usually prefer to have this form, a x minus h quantity squared plus k. This is called vertex form. And the reason it's called vertex form is you can immediately read off what's going on with this function. How? Because notice the quantity in parentheses is squared. And like any squared quantity, it only has two possibilities. It can be 0 or it can be positive. And it can only be 0 when you're actually squaring 0. So when x is 0, this entire thing here will be 0. So you'll just have k. How can you make this quantity 0? Well, you can plug in h for x. So f of h is equal to k. For any other value, this term gets, depending on whether a is positive or negative, bigger and bigger and bigger, or smaller and smaller and smaller. So this point, this h comma k point, is called the vertex of the shape. You've probably all seen this shape graphed before. This kind of shape is called a parabola. And so, for example, if I say y is equal to, say, let's say 2 times x minus 1 plus 1. Oops, squared. Forgot the square. What I see here is when x is 1, this first term vanishes and I just have 1. And that's this vertex right here. As I go further away from 1 in either direction, this term becomes bigger and bigger and bigger. And so the thing expands away from it and becomes a parabola. This shape's called a parabola. If this leading a were negative, it would instead go downwards, as we see now. So this is a wonderful form for a parabola. It tells you exactly what you want to know about it. It tells you whether it opens up or down. It tells you where the vertex is. You can just read it right off. The problem is that how do you get it into this form? Suppose I had, for example, f of x, and let me go back to my notepad. Suppose I had f of x is equal to, say, x squared plus 3x minus 5. How am I going to see how am I going to figure out what this looks like? How do I get it into vertex form? And the answer is you do a stupid trick. The trick works like this. I say, well, I know what a perfect square looks like. I remember the nice thing about vertex form is you had, the only thing involving x was a perfect square. I said, well, what's a perfect square look like? What does, say, x plus a quantity squared look like? And the answer is, well, you can multiply that out using FOIL. That's x plus a times x plus a. And so when I multiply that out, that gives me x squared plus ax plus another ax from the outer and inner terms, so 2ax plus a squared. So when I look over here, I see, well, okay, I've got x squared. I've got 3x, which I guess could be twice 3 halves x, because after all, 2 times 3 halves is 3. But now I don't have the thing I should have now, which is 9 quarters. Where's my 9 quarters going to come from? The answer is, well, what if I just add it in? I know at this point you're saying, what do you mean just added in? That's cheating. There wasn't 9 quarters there before. Where did it just come from? The answer is, yeah, you're right, that would be cheating. But I could also just subtract it right back off again. It's cheating to just add 9 quarters. It's not cheating to add 0. And 9 quarters minus 9 quarters is 0. So now I'm not cheating. And you might say, what? Why? How? This doesn't look like simplification. The answer is no, it's not simplification. It started as simple as it's going to get. We want to get it into a slightly less simple form. So we're in some sense undoing algebra. Rather than trying to grind away all the excess terms to get to the simplest form possible, which honestly is this one, we want to get to a slightly more complicated form that's easier to understand. Because now I can take those first 3 terms and say, well, that's great. That's x plus 3 halves, quantity squared. And what's left over is minus 9 quarters minus 5. Well, minus 5 is just minus 20 quarters, because 20 divided by 4 is 5. So this is x plus 3 halves quantity squared minus 29 quarters. And now I'm in vertex form. Now I can look at this and say, okay, great. The vertex is at minus 3 halves, because if I plug in minus 3 halves, this term goes away, comma, minus 29 over 4, because that's what would be there if I plugged in minus 3 halves. And so that gets me to vertex form. And you say, that seems like a lot of work. I don't want to do that for every single problem. And you're right, you don't want to do that for every single problem. That would be a lot of work. Fortunately, one of the big goals of algebra is to do hard work once and then never again. So how do we do that? Well, let's just take the most general problem possible. F of x is equal to ax squared plus bx plus c. And then do exactly what we just did. Except we're doing it now just with a, b, and c in their most generic form possible. Because then if we want to find out what to do for a specific quadratic function, we can just plug in for a, b, and c, and then we're done. We don't have to do any work at all. This is the usual goal of algebra. You want to do a lot of work once, and then have a formula and never do it again. So what do I do here? Well, let's factor out the a from the first 2 terms. That's a times the quantity x squared plus b over a x. I'll leave the plus c outside because I don't care about it for the moment. That's just some number. Just like I did last time, I say, this looks like the start of a perfect square with x squared plus 2 times the quantity b over 2ax. Notice the 2's will cancel. That gives me that 2 I need from the perfect square formula. So I add in the thing I would like to have as the next term, which is b over 2a quantity squared. And just like before, it would be cheating to just add that, so I'll subtract it back off again. This is not cheating, because now I've just added 0. Because b over 2, I don't know what b over 2a quantity squared is, but I know what b over 2a quantity squared minus b over 2a quantity squared is. It's just 0. And that I can always add. Plus, I still have my c tailing along at the end of the equation. Now, these 3 terms are lovely. That is exactly what I wanted to see. That's just x plus b over 2a quantity squared. Wonderful. There's my nice little piece from completing the square, just like I said before. That's from my perfect square formula. But I still have my little subtracted piece floating around, 2a quantity squared. And then after the whole thing, I still have my plus c. Okay, let's distribute in the a. That's a times x plus b over 2a quantity squared minus, I might as well multiply this out now. This is b squared over 4a squared, but I'm multiplying it in a, so it becomes b squared over 4a plus c. Okay. And now I'm basically done. I've got a formula. I can make it look a little more familiar to people who've worked with quadratics before by putting these over a common denominator of 4a, because then I get a times the quantity, x plus b over 2a quantity squared, minus b squared minus 4ac over 4a. All I've done here is put them over the common denominator 4a, and then subtracted fractions like you always would. And so now we can see something interesting. The vertex, if you're looking at something in standard form, the vertex is just at minus b over 2a. That's really handy. In fact, that's all you really need to know. This formula is more horrible, but I don't usually need to know it, because once I know where the vertex is, I can just plug it in to see what the actual value of the vertex is. So, for example, if I make up another quadratic function, f of x is equal to, say, minus 2x squared plus 4x plus 7, I say, well, where's the vertex? The vertex must be at minus b over 2a. Well, b is 4, so that's minus 4 over twice a. Well, a is negative 2, so that's minus 4 over negative 4, so that's minus minus 1, or 1. So in this case, the vertex is at x equals 1. How high is the vertex? So I can just plug in 1 and see what happens. Get minus 2 times 1 times 1 plus 4 plus 7. Well, minus 2 plus 4 is 2, plus 7 is 9. So the vertex of this parabola is at 1 comma 9. And it opens downwards. Is another cool thing we can see. And we can actually see that. Let's look at that back in our grapher. Let's plug in exactly that formula we just had. So let's plug in that formula. We had, our formula was minus 2x squared plus 4x plus 7. Plot. We have to zoom out a little bit to even see this, because you see it's way up in the air. But there it is, right at 1 comma 9, just like we thought. It's opening downwards, because you notice that leading coefficient is negative 2. And whatever the sign is on the x squared term tells you which way it's going, because that x squared term, as you go far away from the vertex, is going to be controlling everything. So if that's negative, the parabola is opening downwards. If that's positive, the parabola is opening upwards. And that makes some sense if you look back at our notepad again. Look at what vertex form looks like again. This a is sitting out front of this thing that must be positive. So what we see is this thing is either, or must be positive or 0, I should say. So if it's 0, you're just at k. Then as you go away from the 0, this parenthesis piece gets bigger and bigger and bigger and bigger. And then you either multiply it by something positive or negative. If you multiply it by something positive, this whole first term gets bigger and bigger and bigger and bigger. So the parabola opens upwards away from the vertex. If it's negative, this whole first term gets more and more and more negative. So the parabola opens downwards away from the vertex. So anyway, that's how you get between standard form and vertex form. There's a lot more with quadratics. We'll spend tons and tons of time in them in any algebra class. We'll spend even more time on them in calculus. Why do we spend so much time? Because they're the very simplest function that either goes up, turns around, then goes down again, or goes down, turns around, and goes back up again. And it turns out we have to describe things like that all the time. When you throw a ball in the air, as you raise prices for a business, you'll see when you first start raising prices, you make more and more and more money, but then eventually people get sick of it and stop buying your stuff. So you start making less and less money again as the demand goes down. You see it for many, many things. You see it in a simple form for the very bottom of a spring. If you have something on a spring and as the ball goes downwards, it'll hit the bottom of the spring, come back upwards again. It's not a perfect parabola. It actually follows another shape much better, which when you learn trigonometry you'll learn about. But you can approximate the bottom of that spring mass reasonably well with a parabola. In fact, you can approximate the top or bottom of nearly anything that goes up and turns around and goes down again, or goes down and turns around and comes back up again as a parabola. And when you get to calculus, you'll see a whole topic called Taylor series, which says you can approximate any function to a certain extent with a parabola. You could approximate it better if you're willing to use a cubic, better again if you're use a quartic, but you can do it with a parabola. And so we use parabolas really a lot. Well, everybody, this has been Nighttime Mathematics Radio. This has been a pre-recorded version for once because we just didn't have the bandwidth last night. Thanks for tuning in. We'll be back next week. Actually, we'll be back every day next week because of the weird shut-in situation. Good evening, everybody. Have fun doing math.